Hi, I'm Fernando Pereira from UFMG Brazil, and today we shall continue to talk about sparse analysis. We had started talking about it when we saw the SSA representation of programs. We will see that it's possible to generalize SSA to encompass more analysis. Just to remember what's a sparse analysis, let's look again at constant propagation, our last example from the SSA class. Take a look into this program and try to figure out how to solve constant propagation for it. Here's the solution, using a traditional dense analysis. As you see, information is associated with program points. That is to say that at each program point, we need to keep track of the state of variables. As you can imagine, having to keep track of all this information is a bit inefficient. Mostly, it's redundant. Let's see how we can solve constant propagation in a program in SSA form. We have already seen how to do it. Remember that in SSA form, we can associate information directly with a variable name, because the state of that variable will never change along its life range. That only works in SSA form. For instance, in this program, variable A is constant at some points and non-constant at others. Can you check that this is true? But once we are in SSA form, each variable has a unique abstract state. Notice that we no longer have a single variable A in this program. Now we have A0, A1, and A2, and they do not have all the same abstract states. A0 is constant, for instance, but A1 and A2 are not. So, in SSA form, instead of having to keep track of the abstract state of every variable at every program point, the solution of our analysis is much simpler. It's basically a table that associates abstract states with variable names. You can see this table in this figure, and you can see that the abstract state of A0 is constant 1, whereas the abstract state of A1 and A2 is NAC. As you can see, the SSA form approach yields a much more concise solution. We are actually reducing the asymptotic complexity of both running the analysis and keeping information. So the SSA conversion, in the case of constant propagation, improves the algorithmic implementation of the analysis in both time and space. What SSA form is doing is to transform constant propagation into a sparse analysis. In a sparse analysis, we associate information with variable names. That's in contrast with a dense analysis in which we associate information with pairs, formed by program points and variable names. But there is something more. A sparse analysis must not use trivial transfer functions. Let's see what is this. If a transfer function changes information, then it's not trivial. In other words, trivial transfer functions are like identities. For instance, in the case of constant propagation, the transfer function associated with an assignment is non-trivial because it changes the state of the variable on the left side. However, the transfer function associated with an instruction that defines nothing, like a statement to print stuff, for instance, is trivial because the information that enters it is the information that leaves it. The key to have sparse analysis is something called live range splitting. This is a way to reduce the live ranges of variables. Basically, to split the live range, we insert copies in the program. These copies create new names of variables. Then we rename these new names, so that we ensure that every definition dominates its use. Remember, for an analysis to be sparse, we need to ensure that information associated with each variable is unique. To ensure this property, we split the live range of variables, where new information can be associated with that variable. Also, we need to split live ranges where information collides, because the collision of information might create new information. Remember that whenever information collides, We use the meet operator to know what will be the new abstract state that will appear. Now, something interesting. If we split live range between every two pair of instructions, then we automatically have a sparse analysis. Can you figure out why that's so? Stop the video and think about it. Try to remember what's a sparse analysis. Well, if each variable has a very short live range that only exists across one instruction, then there is no time for the information associated with it to change, basically. However, that's not the right way to produce a sparse analysis. Can you think on why that's a bad idea to split the live range of variables in between every pair of instructions? The thing is that if we split live range between every pair of instructions, as I said before, then we end up with too many trivial transfer functions. For instance, in this example, the state of variable A does not change between an assignment to B2 and an assignment to C3. Here we are talking about constant propagation. These assignments have no effect on variable A, and yet we have a copy from A2 to A3 to do the live range splitting. And the transfer function associated with the copy is trivial in this case. You can see its equation right on the left side of the figure. But then, where do we split live range then? The answer to this question, where we split, will be the subject of the next class. But notice that we are associating points in a lattice with the live range of variables. And we want these points to be invariant along all the live range. When this property is true, we say that the dataflow analysis has the single information property. So we need to split live range to ensure that the single information property holds. The different strategies that we can use to ensure the single information property is the subject of the next class. Till there, you feel free to drop me an email with questions or comments. Thank you.